Hello friends, welcome to GT Science tutorial. In this video, I'm going to explain about the heat capacities. There are two types of heat capacities, specific heat capacity and molar heat capacity. We have already learned about specific heat capacity in secondary level. Specific heat capacity is defined as the amount of heat supplied to 1 gram of a substance to increase its temperature by 1 degree Celsius. Now it's time to understand about molar heat capacity. So in this video, we are going to understand what molar heat capacity actually is, what are its type, and if there is any relation between them or not. So let's start. Let us consider there is a substance whose mass is m and that is a temperature T1 and it is gaining dq amount of heat, then its temperature will be T2, right? So here what we can write, the heat energy gained, that is dq, is directly proportional to the mass of the substance. Let us consider it to be equation number 1, that is if the mass of the substance increases, then it will gain more amount of heat energy. Let us consider it to be equation number 1. Similarly, the gain in heat energy is directly proportional to change in temperature, that is dt. That is equation number 2, where dt means, yes, you are correct, T2 minus T1. So, if the change in temperature is greater, that means the gap in T1 and T2 is greater, then the amount of heat energy gained will also be greater. Now, we can combine these two equations. What will happen if we combine it? Combining 1 and 2. Then, we can write dq proportional to m into dt. Now we know that if we remove this proportionality sign, then we have to put a constant over there. So we can write dq is equal to m into c into dt. Here this c is equal to proportionality constant, that is called heat capacity. Now, if we rearrange this equation, then we will get C is equal to dq by m into dt, right? Similarly, we can write C is equal to dq by dt if mass is equal to 1 gram or 1 mole. Now, here I have written two units, gram and mole. Gram is for specific heat capacity and this mole is for molar heat capacity. That is, if the amount of substance is given in gram, then we are talking about specific heat capacity, and if the amount of substance is given in mole, then we are talking about molar heat capacity. So if we put the value of m to be 1 mole, then this equation becomes this, C is equal to dq by dt. Now let's see the types of molar heat capacities. There are two types of molar heat capacities. They are molar heat capacity at constant pressure and molar heat capacity at constant volume. This is represented by Cp that I have written over here, and this is represented by Cv that I have written over here. Now let's understand them one by one. First of all, let's talk about molar heat capacity at constant pressure. Molar heat capacity at constant pressure simply means the amount of heat supplied to the substance at constant pressure. Let's understand this mathematically. We know that the heat capacity of the substance is given by the equation dq by dt if 1 mole of the substance is taken, right? Let us consider it to be equation number 1. Okay, from first law of thermodynamics. What is the first law of thermodynamics? Yes, you are correct. dq is equal to d plus p dv. where this E is equal to internal energy, right? E is called internal energy. P is the pressure. dV is equal to change in volume. Or simply we can say that this P times dV is the work done, right? Now, let's consider it to be equation number 2. From 1 and 2, from these two equations, if we put the value of dq to equation 1, then we get C is equal to dE plus P dV by how much? dt, right? Let's separate them. So it will be dE by dt plus P into dV by dt, right? So we get this much. Let's consider it to be equation number 3. At constant pressure, this equation can be written as Cp is equal to dE by dt P plus P into dV by dt P, right? So this becomes equation number 4. At constant pressure, the value of heat capacity will be equal to this much. Now, we know that the enthalpy of the substance is given by the formula E plus PV. I have already made a video about enthalpy. If you haven't watched that video already, please check the link in the description below. You will find the link over there. Now, let's differentiate this equation with respect to temperature at constant pressure. Then what do we get? Differentiating with respect to temperature at constant pressure. Then we get dH by dt at constant pressure. P is equal to dE by dt at constant pressure. P plus P is constant, right? So it will be dV by dt at constant pressure P. Let us consider it to be equation number 5. Okay. Now, if you see equation number 4 and 5, then the right hand sides are equal, right? So from 4 and 5, what do we see? Cp will be equal to how much? Yes, you got it correct. So dH by dt P. So this is the required answer. Here, what do we see? The molar heat capacity at constant pressure is equal to the change in enthalpy with respect to change in temperature at constant pressure, right? So let me write over here. Molar heat capacity at constant pressure is equal to change in enthalpy with temperature at constant pressure. So this is the definition of molar heat capacity at constant pressure, which is equal to the change in enthalpy at constant pressure with respect to the change in temperature. So this is the complete derivation to get the value of molar heat capacity at constant pressure. Now let's understand the molar heat capacity at constant volume. To understand about molar heat capacity at constant volume, let me write the formula of heat capacity one more time. That is C is equal to dQ by dt, right? Where dQ is the amount of heat supplied to the substance and dt is the change in temperature. And according to first law of thermodynamics, we know that dQ is equal to d plus P dV. So we are putting this value over here. This becomes C is equal to dE plus P dV by dt. If we separate it, then how much do we get? dE by dt plus P into dV by dt, right? At constant volume, dV will be equal to how much? 0, right? dV, that is volume will not change. Then it becomes Cv, that is molar heat capacity at constant volume, is equal to dE by dt at constant volume, right? Because this whole value will become 0, and this is the required expression for molar heat capacity at constant volume. It is actually easier to find out as compared to molar heat capacity at constant pressure. That means molar heat capacity at constant volume is equal to the change in internal energy with respect to temperature at constant volume. Let me write that. Molar heat capacity at constant volume CV is equal to the rate of change of internal energy with respect to temperature at constant volume. So this is the definition of molar heat capacity at constant volume. That means it is the rate of change of internal energy with temperature at constant volume, right? Now we know what molar heat capacity at constant pressure actually is. We know what molar heat capacity at constant volume actually is. Now let's see the relation between Cp and Cv, if there is any relation among that. We can establish the relation between Cp and Cv from the formula of enthalpy, that is H is equal to E plus Pv, right? Let's consider it to be question number 1. From ideal gas equation, we can write Pv is equal to nRT, where this R is equal to universal gas constant. For n is equal to 1, this value, that is Pv, can be written as RT, equation number 2. Now from 1 and 2, in place of this Pv, we can write RT. So H will be equal to E plus RT. Let's consider it to be equation number 3. Now let's differentiate this equation number 3 with respect to temperature. Differentiating equation 3 with respect to temperature, then what do we get? dH by dt is equal to dE by dt plus R into dt by dt. Now we know that the change in enthalpy with temperature is called Cp. The change in internal energy with temperature is called Cv, plus R into dt by dt means 1. Now we can take this Cv to this side and it will be Cp minus Cv is equal to R. And this is the relation between Cp and Cv, that is Cp minus Cv is equal to R. This formula is very important for numerical problem as well. Now you might be wondering about which value is greater, Cp or Cv. Then there are two ways to tell the answer. First, by logical explanation, another mathematical explanation. Mathematical explanation can be done by seeing this formula. The value of R is always positive. It is the universal gas constant and it is always positive quantity, and to give it positive, the front value must be greater, right? So Cp is always greater than Cv. Because R is always a positive value. This is the mathematical answer. Now there is a theoretical answer as well. That is, we know that Cp is equal to dH by dt, right? And Cv is equal to dE by dt. dH means what? We know that enthalpy is equal to E plus Pv, right? So what do we see? At constant pressure, the amount of heat supplied is utilized to do two work, to change the internal energy as well as to do the work. But in another case, at constant volume, the heat supplied is only used to change the internal energy. That means it doesn't have to do any work. So to do work, it needs more amount of energy. So that's why the value of Cp is always greater than the value of Cv. So this is what molar heat capacity actually is. I hope you understood everything about this video. That's all in this video. If you like the video, please share this video as much as you can, and thank you for watching the video.